Let's begin our course for conformal field theory with the topic of conformal generators. So recall if you have studied quantum field theory, and of course I would expect all of you to have studied quantum field theory before you start studying conformal field theory, right? And for obvious reasons, because again, conformal field theory is a type of a quantum field theory, right? As we have discussed in the introduction video. Right. So we know that we have a group that is known as the Lorentz group. And we know that this Lorentz group consists of Lorentz transformations. So Lorentz transformations, and it also consists of rotations, right? So rotations and composed with Lorentz transformations make up what is called the Lorentz group. So we can define this group or the metric for this as or the transformations that this Lorentz group will have as G is equal to lambda transpose times G lambda, right? So if I sandwich G between lambda transpose and lambda, and I get back my metric G. So this has to be satisfied. Now, here these lambdas are just some these are the, you can say that these are the transformation or transformation matrix, right? Transformations, these are matrix or matrices, right? So well, now this is Lorentz transformations and rotations. What about conformal transformations? So we have a question where we could ask what are conformal transformations, right? So I'll just use CT for conformal transformations just to avoid writing it down so many times. So, well, we can define conformal transformations in a way which is, we could say, how would these transformations change the metric tensor, right? So what these transformations do is they'll transform the coordinates and your fields. So I can define the conformal transformations with this thing, that the metric tensor, the transformed metric tensor, is simply this transformation which is a function of a coordinate, right? So this conformal transformations, they are a function of a coordinate, and this thing times the original metric, which is g mu nu. Now the condition over here is that the metric should not vanish, right? So this transformation should not vanish the metric tensor, or it should not be it should not make it negative, right? So we'll say that the condition is with lambda of x is greater than 0, right? Now this is going to have some consequences, if you will, right? And so we'll discuss those consequences now. Some of the consequences for this thing is that, well, you can say, you can ask, how would the metric tensor transform? This is something that we already know. If I ask a question that how does metric transform, but generally, right? So how does it transform in general? Well, we know from our study of both quantum field theory and general relativity, we know that we can transform, we can write the coordinates. First of all, we'll work with the coordinates, right? So we know that if I have some x mu, and now let's say that I add some infinitesimal quantity to this thing. Let's say that it's epsilon mu, but this quantity is a function of x, right? So what that means is that this this addition or this translation, it is dependent on the variable x, and hence then it's just any arbitrary transformation, right? So of course the condition is that this is small, right? This is a very small number. All right, so this would give you x prime mu. All right, so from this I can do something. Let's factor this thing for this thing, right? So let's make this thing the subject of our equation, right? So it's x mu is equal to x prime mu minus epsilon mu of x, right? So I have just rearranged this thing as this. All right, now this is something that I need, so let's just take it to the next page. So let's do this thing. All right, so here we have it. Okay, so now if you have studied tensors, you know that you can borrow this thing from tensor analysis. That the metric tensor transforms as this thing. You can write it as lambda alpha mu lambda beta nu times g alpha beta, right? Where this thing lambda alpha mu is just a partial derivative of x alpha over partial x prime mu, right? And so the rest of the lambdas will follow from this thing. Of course, I expect you to know a tensor analysis if you are learning this course, right? Because of course tensors will be used very intensely in this course, the tensor calculations and everything, right? So we'll be dealing with these indices. We'll be, you can say, doing index gymnastics, if you will, a lot in this course. All right, so now if I write this in terms of partial derivatives, g prime mu nu, I can write this lambda as partial x alpha over partial x prime mu, and this thing as partial x beta over partial x prime nu times g alpha beta. All right, now note that this thing is important, because if I look at this thing, I can easily compute both of these partial derivatives, right? So let's compute these partial derivatives using this function. All right, so I can see that this first one, partial x alpha over partial x prime mu, what would that be? Let's see from this thing, right? So that would simply be, so this is partial x, this thing is prime mu, right? So partial x prime mu over partial x prime mu will just be a delta function, right, with alpha and mu. So when these indices are same, then this would give you 1, otherwise it would just give you 0, right? So that's from tensor analysis, or it's a basic calculus, right? Okay, so the next term is this thing, and what would that be? That would simply be partial this thing, right? I can use a shorthand notation, and I can say partial mu of epsilon mu, right? But this is a function of x. Let's write it this way. So the indices, we have to always take care of our indices, right? So let's write alpha over here, because we are applying this partial x alpha, right? So this would be alpha. All right, so that's this. And similarly, you can compute this other derivative as well. And then putting these back into your equation, this would give you g prime mu nu as the first one is this one, delta alpha mu minus partial mu epsilon alpha. And then the second one would be, you'd compute this derivative in the same way. So upper index is beta. So wherever I have alpha, I'll just replace it with beta, just a shorthand trick. So this would be beta nu minus partial nu e epsilon beta. All right, and then I have g alpha beta. All right, so this is something that we have so far. What can I do from here? Let's make this a bit more well understandable, right? So to do that, let's just multiply these two brackets, right? So if I do that, this becomes g prime mu nu is equal to, let's multiply this with this, and so this would become delta alpha mu delta beta nu, and then you have this thing g alpha beta, right? So g alpha beta. Okay, that's the first term. Now what would be the second term? Second term would be delta beta nu times partial mu this thing, right, with a minus sign, of course. So that's delta beta nu partial mu epsilon alpha, and then you would have your g alpha beta. All right, and then the next term would be minus partial minus delta alpha mu, right, minus delta alpha mu partial nu epsilon beta, this thing. So this is delta alpha mu partial nu epsilon beta g alpha beta. All right, and then we would have another term which we are going to ignore really because it's a higher order term. I'll tell you why. You'd have this thing, right, partial this thing, and this thing. So that would be partial epsilon squared, right? Something like this. All right. Now, because remember that I'll write it over here, right? So let's write it over here. We remember that epsilon is small, right? So what that means is epsilon is much smaller than 1, and if that's the case, then it would be somewhere around 0.000 something. And if I square this thing, if I take a square of this thing, it will be even small, right? And so if it's so small, then you can just, get rid of it. So we'll just neglect this term. All right, so if I neglect this, then if I now do some contractions really, right? So what's a contraction that I can do over here? I know that this thing, I can contract beta alpha, and then I'm left with mu nu and this thing. So that just gives me g mu nu. So that's my first term. Let's do some contraction over here. So I see I have, let's see what indices do we have. Beta over here, so this, and we have a beta over here. So this thing would give me a partial mu and epsilon alpha, this would make it epsilon nu. Okay, we have to be careful with our indices. This would be partial mu epsilon nu, and yeah, and the last term would be partial nu epsilon mu. All right, so now that's your g prime mu nu. We can write it like this: g prime mu nu is equal to g mu nu minus, and let's write this term in brackets, partial mu epsilon nu minus, now we will have plus partial nu epsilon mu. All right, okay, so I have ignored this epsilon as a function of x in writing, but you have to remember that epsilon is function of x, right? So you have to keep this in mind. Remember that. Okay, so now this is a function that I have or an expression that I have for the transformation of g mu nu. But now if I want a conformal invariance, that's something that I'm looking for, right? Because we are dealing with conformal transformations. And for conformal invariance, the new metric tensor g prime mu nu should be proportional to the initial metric tensor g mu nu. Why, you ask? Well, of course, because we know of this transformation that when I transform my metric tensor, it is just some transformation matrix, which is a function of x, times the metric tensor, right? Because of this thing, this has to be true. Right. Now, if that has to be true, then this means that this entire thing that I have over here has to be or must be proportional to this metric tensor g mu nu. So let's, or I think we can write it over here. Let's write this thing right? So this is g mu nu. Well, that's g mu nu, right? So this is the term that I'm looking at. So this term partial mu epsilon nu plus partial nu epsilon mu, this has to be proportional to the metric tensor g mu nu. So that's not an alpha, that's just a symbol for proportionality. Remember that. All right. So that's something that I'll be taking with me on the next page. So let's just copy this thing. All right. And then we'll see what we do with this thing. Okay, so let's put it over here. All right. Okay, now if you look at this expression, you can see that this thing became from conformal invariance, right? Conformal invariance, which means that conformal invariance basically imposes a condition on this thing, which is such that this thing partial mu epsilon nu plus partial nu epsilon mu, it has to be equal to of course this g mu nu, but the constant of proportionality is not just a constant really, but it would be a function of x, right? Because remember, our epsilon was a function of x, right? So this epsilon is a function of x. All right. So if this is the case, right, if that's the case, then if I go back and if I look at this thing, g prime mu nu, well, actually, let's bring this in front as well so we can write something. All right. So let's put it over here. Okay. So here we have it, right? So you can see that this thing is equal to f of x times g mu nu. And here I have this g prime mu nu as g mu nu minus partial mu epsilon nu plus this thing, right, which is this thing. So let's just write it like this. All right. Now, if you remember, how did I define this thing? My conformal transformations, right? We said that g prime mu nu is going to be equal to lambda of x times g mu nu, right? And that's how we defined our conformal transformations, right? Now, if I look at this thing, right, and if I look at these two things, then I can clearly say that this lambda of x should be equal to something, and that something should have a function of x. So this is equal to 1 plus f of x, right? Because I have this thing, then I have this thing, but this thing is just f of x times g mu nu, right? So I can factor out g mu nu. I can write this thing as f of x times this thing, right? So actually let me try to tell you, write it down. How do I get this, right? So we see that this is g prime mu nu is equal to, now I can factor out this g mu nu from this, because I can replace this thing with f of x times g mu nu. So I get 1 plus this f of x and then g mu nu, but I can factor that out, right? So g mu nu, and then that's this thing. Now because of this thing, my lambda of x, if I compare these two, right, then my lambda of x is just 1 plus f of x, and that thing is satisfied. All right, good. Okay, so having this, then what I can do is, if I look back at this equation, partial mu epsilon nu plus partial nu epsilon mu, which is equal to f of x g mu nu, right? Now let's contract mu and nu, right? So when I do that, I can write this thing as partial mu epsilon mu, and I can write this thing as partial mu epsilon mu, and this is equal to f of x g mu mu. All right, but what do we know about this thing, right? This thing, what is this thing? This thing just gives you the number of dimensions, right? The number of dimensions of the space where this metric tensor is defined. So what I can write from this thing now is that this thing is just 2 times, well, if I see this thing partial and epsilon, mu 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 mu, right? This thing is defined as a dot product of partial and epsilon, but it is 2 times, so I just write this 2 times partial dot epsilon. And on the right hand side, I have f of x times the number of dimensions. Let's write it with small d. So this becomes d times f of x. Remember, this d is the number of dimensions of the space. All right, so having this at our disposal, this, now we can write your f of x. The function is now defined from this equation, and that is 2 over d times the dot product of partial and epsilon. Amazing, right? Now having f of x from here, I can finally write down this equation, this one, right? This one, this equation, let's rewrite this as partial mu epsilon nu plus partial nu epsilon mu is equal to f of x is, this f of x is 2 over d partial dot epsilon times g mu nu. So let's just box this equation, right? And this equation is a very important equation, really. This equation is the condition for conformal invariance, right? So it's the condition for conformal invariance, right? Now, of course, we know that this epsilon, it is, you can think of it as the deformation of the coordinates, right? Remembering how it was defined over here, we defined it as some deformation in the coordinates of over here, right? In x mu, it was some deformation in x mu that transformed to x prime mu, right? So that's that. And we can say that this this equation implies a constraint which is imposed on this epsilon by the conformal invariance. So this equation was very important, and this equation is known as the condition for conformal invariance. It's one of the equation that talks about the condition for conformal invariance. In the next lecture, we'll be using this condition and we'll be deriving some more equations from this equation, some more, you can say, useful relations, which we'll be then using in writing down the conformal generators. So this is part one of the first topic, conformal generators.